All right, just a video to take you through chi-square procedures. And we'll work on a one-way chi-square and a two-way chi-square. This corresponds with page 30 in your note packet. All right, so we use chi-square when we're dealing with population proportions, but more than two populations. So there's two ways that we can kind of deal with that. One would be, well, the one-way chi-square, which is you have population proportions for different categories and you want to see if they're the same or equivalent, roughly the same throughout each category, or if there's a significant difference for at least one of them. All right. The other one is a two-way chi-square, which is kind of the same idea, except you'd have two variables that you're comparing against one another. And we usually use that to test for independence. All right, so like I said, we're going to focus on a one-way chi-square to get started. You have conditions and assumptions just like any other hypothesis test: simple random sample, 10% rule, and expected, this is new, expected cell frequency condition. We must have at least 5 individuals or entries in each cell. And that's just basically, I mean, at this point, we just kind of assume that the test won't work properly if that's not satisfied. All right. The process: name the test, determine the expected values based on the context of the problem. We'll get to that. Address the conditions, state the null and alternative hypotheses, state the test statistic, degrees of freedom, critical value, and p-value. Determine the relationship between p-value and the alpha. So that's if the p-value is less than the alpha, you reject the null. If not, you don't. And then state the conclusion using complete sentences. All right. So I have the excerpt from the AP formula sheet. I have a solved example here for you, so you can take a look at that. All right, but let's tackle an actual problem. All right, they're all actual problems. I mean, one where I'll guide you through it. All right, so the example in an Associated Press report, it was reported that in a random sample of 830 stolen cars, 140 were white, 100 were blue, 270 were red, and so on. Suppose the American Automobile Association reports that 15% of all cars are white, 15% are blue, 35% are red, and so on. Conduct a hypothesis test to answer the question: does car color affect the chance that it will be stolen? And use an alpha value of 0.01. So this would be a one-way chi-square. But let me show you in the inference app. If we go to tests, you'll see, you'll see chi-square, and you'll see test. All right, you have the goodness of fit test. There's something weird here where it says chi-square, then it says t-test. I don't know why that's like that. I'm sure they're going to take care of that in some future update. The chi-square test isn't a t-test. Right, so you could ignore that, which is, unfortunate, because I've been telling you all along, like, look at the gray. It'll help give you an idea of what kind of test you're using. But do not write chi-square t-test, right? If you hit OK, you see goodness of fit, homogeneity, and independence. At the top, you see chi-square test goodness of fit. We always name the test. It's very easy to get lazy in that regard. But since NumWorks is telling you flat out what the test is called, like, there really is no excuse. Right? Now, on paper, I'm going to indicate the relevant values here. So I'll make a little table. We have 830 stolen cars. Just do it over here. 140 were white, so I'll say white. 140, 100 were blue, red 270, black 230, and other 90. All right, so like I said, I'll make a little table out of this. The first group here we're going to call the observed, and the second group is going to be the expected. We don't have any information for the second one numerically yet, but we will in a second. All right, so they gave us percentages, but we need to have it in line with the 830 stolen cars. All right, so when they say 15% were white, it's 15%. Well, it's 15% of what? 15% of 830. So let me put my observed values into the calculator. As data entry goes, it's not as terrible as some other cases. It's not bad at all. It's only typing in 5 values. But then under expected, I'll do 830 times 0.15. All right, they want you to indicate the expected values on paper. All right, so make sure you do that. So whatever you put in the calculator, also write down. 15% are blue, so that should be also 124.5. 35% are red, so 0.35 again times 830. So 290.5. 30% are black, so 249. And 5% are other colors. All right, so 0.05 times 830. Oops, 0.05 times 830. So 41.5. All right. Now, personally, I like to do a quick double check. 124.5 plus 124.5 plus 290.5 plus 249 plus 41.5 adds up to 830. So I'm confident that I didn't just totally botch this. All right. So get back in here. Degrees of freedom, it says that there's 4. Degrees of freedom in this context is K minus 1. K is the number of categories. All right, so in this case we have 1, 2, 3, 4, 5 categories. So 5 minus 1 is equal to 4. All right, you're not always going to have to state how you came up with that value, but you should be prepared to. All right, so I always err on the side of giving the number. Using a formula is a good thing in some cases, unless you're not confident that you're using a formula that's correct to that problem. So, if you're in doubt, I guess don't write the formula, just write the number. But there's enough ways for you to kind of piece together, okay, where do you suppose that 4 came from? Well, I have 5 things minus 1. Normally, degrees of freedom is n minus 1, number of items in the sample. Here, it's really number of samples, right? So it's kind of a little bit of a difference there, but it's not too far away that it would be completely foreign. They said to use a 0.01 level of significance, so alpha is 0.01. So I scroll down, pop in my 0.01, hit next, and it gives me a test statistic. The thing that makes this inference test, specifically in the calculator, very different from what we were doing is, even though we have to state the null and alternative hypotheses, they didn't ask us to do that in the calculator. All right, so I got my test statistic and my p-value, and it almost seems like, well, these can't be right because I never told it what to test for. But when it comes to goodness of fit, there's really only 2 possibilities. One is that your null hypothesis is that the sample distribution is a good fit for the population distribution, which is quite a mouthful. Just jotting this down real quick. The other is that all the population proportions are equal to one another, which is a little easier to handle. So if I say HO, I could say, I'll write the other one, the one I just kind of blurted out, but so sample distribution is good fit for population distribution. All right, and that would actually make more sense in this case than saying that all the population proportions should be the same, right? Because it's not really the case, because we're testing, well, first off, we're testing to see if there is a meaningful difference in the population proportions between white and blue and red and so on. I don't, let me see here. I don't think it said anything about what the ulterior motive is, but just looking at the numbers, I would probably think, it wouldn't be unreasonable to say that they're probably trying to make the claim that if you have a red or a black car, your car is more likely to be stolen, right? So the proportions for each one, not necessarily going to be balanced, because just by the percentages, 15% of all cars are white, 15% are blue. They're basically saying, are cars getting stolen at a rate that's disproportionate to what the distribution of car colors are, right? So if there are 830 stolen cars, about 290.5 of them should be red, right? Is this distribution far enough, the sample distribution, the observed values, is it far enough away from those expected values to say, well, I don't think those percentages were right, right? So my alternative, almost simplistic, is sample distribution is not a good fit for the population distribution. Now, if those percentages weren't there, if they didn't give us these values, you wouldn't really have anything to go by except to say that each one is equally likely to be stolen. So if they didn't tell us that American Automobile Association information, I would say, well, there's 5 categories, then 20% of stolen cars should be white, 20% blue, 20% red, and so on, right? In that case, I would write my null and alternative hypotheses as what you see here, just with a equals P5, right? So this is nicer to write, but it's not necessarily relevant in all cases, right? And just going back to this one here, if you read through this example, you see that if the null is not true, it doesn't mean that each of the P's are different from each other. It means that they're not all equal, which means maybe the first one is not equal, but the other 3 are. The second one is not equal, but the other 3 are, and so on. Every different possible way in which you could have equality among the 5, in the example we're working on, 5 items, right? So that's a little bit of a difference. But we have our p-value, we have our test statistic. P-value is incredibly small. So whatever the alpha value is, p-value is going to be less than whatever that alpha value is, so we reject the null hypothesis. So get rid of the null. The alternative is the one that we're going with, right? And again, I use the X and the check. I'm saying that the one that I put with the check is more likely to be true based off the sample data than the one I put the X. I'm not saying like one's right, one's wrong definitively, right? It's just one is more right, right? Based off the sample data. So then the only thing that's left is the conclusion, right? So I would say, does car color affect a change? So we have enough evidence to say that car color affects the chance that it will be stolen at the 0.01 level. Right. I could also look at the picture of the graph. All right, just remember, I know it's hard to see on these numworks, but that slanted lines, that form of shading is associated with the alpha. If that p-value is contained within that shaded alpha region, that's another way that we would say that we're rejecting the null. All right, so I can just do a quick sketch of that there. And since the calculator gives you a sketch, it's never a bad idea to include that. You'll notice that it's skewed to the right, starts off at 0, right? It's only positive values, or sorry, non-negative values, right? And then somewhere over here around 11, or maybe 13, sorry, I was looking at the wrong side of it, 13-ish. So if they scaled it, they went by 4, so 4, 8, 12, and then somewhere over here is where the alpha rejection area, that's where it lives. That's alpha is equal to 0.01 with degrees of freedom of 4. Now, somewhere way off the screen to the right is where that p-value is living. It's capturing such little percentage of the population, of the area, I should say, that it's not even on the screen. So it's so far into this shaded region that it's like over here somewhere, right? So if that's the rejection area and your p-value is putting you in that rejection area, then it must be the case that we reject the null. Not always necessary to include this, but it could come up, and better safe than sorry, especially if the calculator is giving it to you. Now, if you need that particular number, let me go into the distributions app. You see that there's a chi-square. All right, so if they ask me what the critical chi-square value is, critical value for chi-square, I go in here, tell it the degrees of freedom, and then just make that top little heading area look like it's supposed to look. So what I mean by that is I'm looking for something that's shaded on the right side. So I grab this one. This tells me what the probability is that any chi-square, they say x here, just I think because of the ability or inability to use appropriate characters. But they're saying x is greater than or equal to 0, that's everything. If I change that to a 1, for example, you can see that it's working its way over. I make it a 12, all right, so you're getting closer and closer to a 0.01. Now, if I want that perfect number, what I do is I put the 0.01 here, hit OK or execute, and it'll tell me what that cutoff number should be. So 13.277. And so we can compare the test statistic to that critical value, right? Because basically, anytime we do a normal curve or a chi-square distribution, it's just a glorified number line. I'm just asking, all right, well, where does that 66.329 fall in comparison to 13.277? 13.277 is the cutoff for the don't reject the null region, which is the non-shaded, and reject the null region, which is the shaded. So this is 66.329 is very far into the reject the null region, right? So that's another way that you can draw the conclusion that we're rejecting the null hypothesis. All right, so just to keep that in mind. And also chi-square distributions are always going to be right skewed and right tailed. So you only have to worry about finding that one value on the right-hand side. So the last thing that we're going to cover is the chi-square test for homogeneity and independence. Calculator can handle that too, which is good. Same conditions and assumptions. I mentioned before that when we deal with two-way tables, that's two variables that we're looking to relate to one another. So it's really a test for independence to see if those two variables are dependent on one another or independent from one another. All right, but procedure-wise, name the test, use the inference app, address the conditions, and so on. All right. I gave a quick example of what a two-way table looks like. Say if we were breaking it up by Oh, look at that. I had a little typo here for somebody. This should be freshmen and seniors. Same mistake over here. I changed the context, modified the data, and then I just forgot to change the labels. So, well, at least I'll know who watched the video based off of how many people submit this for a typo bonus. So a question that you might be asked is, at the 1% level, do these data provide evidence of an association? We say association or relationship between the two variables, political philosophy and grade level. All right. So I carry you through the conditions, setup, calculations, and all that stuff through this guided example. You see the null and alternative hypotheses are that there's no relationship versus some relationship. And then the other possibility is, depending on how they phrase the question, no relationship or independent. If there's no relationship between two things, they are independent from one another. If there's some relationship, then we would say dependent. All right. Now, it doesn't mean it's causal, doesn't mean one causes the other to happen, but there is some kind of relationship, and that's where we would start. So I gave you some screenshots on how to get through this. This is in the inference app again, under tests, still chi-square, but this time homogeneity and independence. And then you can see that we just pop the values in, and it'll give us the test statistic, degrees of freedom. Degrees of freedom is based solely on the table, really. It's the number of rows minus 1 times the number of columns minus 1, not including headings or totals, so ignore those. Just basically the meat of the table. You have 2 rows, 3 columns. So the degrees of freedom would be 2 minus 1 times 3 minus 1. So 1 times 2, which is 2. All right, so you can get it manually also. You don't have to type in a bunch of data in order to figure out degrees of freedom. Then it'll tell you the critical value, the p-value, just like I walked through with the one-way chi-square. Same idea. Draw a conclusion, and off you go. All right, so let's do one that's slightly beefier. So a sport preference poll yielded the following data for students at a local high school. Use a 5% significance level and test to determine if sport preference and class are independent. All right. So my null and my alternative hypotheses. You can do conditions first. I kind of go back and forth on that. Sometimes, like the last thing I see in the question is like the first thing I want to do on paper, and they're saying test the claim. So I just grab this right here, word for word, and say sport preference if I could actually write. So preference and class are independent. Then sports preference and class are dependent in some way. I use that phrasing, dependent versus independent, because that's what they asked. Right? I could also have written it as there's no association versus there is an association. But then later on in my conclusion, I'd have to take that additional step to tie no association to independent and some association to dependent. It's an extra step that I don't really want to get into. Conditions, same as before, simple random sample. All right, it's at this moment that I realize I glossed over that over here. All right, but it's simple random sample, 10% rule, and expected cell frequency condition, so at least 5 per cell. All right, so 10% rule and expected cell frequency. All right, well, I don't have any expected values yet, but we'll confirm that in a minute. It doesn't say anything about a randomization, so we're going to assume that. This is data for students at a local high school. It all depends, right? So if we're only drawing a conclusion about this high school, then I don't know that I could confirm that the 10% rule would apply. But if I'm trying to draw conclusions about all high schools in general or all high schools in Westchester County, like whatever I can think of, just beyond the one high school, then I can assume this, all right? And again, for each of these, just give a brief statement. We're assuming because it's not explicitly stated in the problem, and for a simple random sample, for the 10% rule, we're assuming it because if we have a need to draw conclusions about the greater population of high school students, I can reasonably assume that there's more than 200 freshmen, I could say in Westchester, in New York, in the Northeast, in the country, more than 200 freshman basketball players, and so on, right? But at this point, we'd have to assume all that. Now, the expected cell frequency, there's ways to compute it by hand. It's not pretty. It's basically taking whatever the total is for the row that a number is in. So let's say this 20. If I take that row total and multiply it by the column total and divide it by the grand total, that would get me the expected cell frequency, which is not something that most people want to do. I'm just double checking. I don't even think I put that formula in here. Oh yeah, there it is. So you could use the formula, but you can see the difference between working with a 2x3 table versus working by a bazillion table. So I'm going to say that you probably don't want to have to do it that way. The trade-off is that you have to type the information in, so we start doing that. All right, so we have all those values. I go to next. It'll give me my test statistic. Chi-square 28.498. My p-value 0.0549. So this is in the that gray area for p-values. All right, so p-value is greater than alpha, so do not reject the null hypothesis. All right. Now, when you're looking at the expected values and the observed values, you see that in most cases, they're not too far away from one another. There are some exceptions, like, unless I wrote it down incorrectly, but sophomores playing basketball, right? That's, so second row, first column. The observed value is 42, but the expected value is 27.4. All right, so those aren't really close to one another, but overall, I'd say most of them are in the right neighborhood. All right, so what we're looking for here is a determination of whether there's such a striking difference between not just one or two of the cells and their expected value, the observed and the expected, but a good amount of them to cause doubt on whether or not those variables are independent of one another. All right, so do not reject the null, so we keep the null, ditch the alternative. All right, so we can conclude that sport preference and class are independent. At the 0.05 level. And it's for these gray area p-values where you're like, hopefully aware of the fact that depending on what that alpha value is, you may get a rejection or a fail to reject. This is ever so slightly bigger than 0.05, so it's right on that bubble. But if I were working with a an alpha value of 0.10, then it would reject and we draw the opposite conclusion. All right, so just got to be careful about that. So I'll make a little note here. I'll throw it in wherever degrees of freedom is equal to 18. Get my picture. You can see here, now again, it's skewed right, although it doesn't seem as skewed right as the other one. I mean, it certainly isn't as skewed, but there definitely is a little bit of skew to it. So let me get that in here. But you can see what I was talking about before, that the p-value, which is the orange shading, is not contained within the alpha value. So the alpha value, again, is talking about the cutoff, or it's indicating the cutoff between the rejection of the null and failure to reject. If it's contained within, if the p-value is contained within the alpha, then we would reject the null hypothesis. But it burst free and it's beyond the alpha, so we fail to reject the null hypothesis, right? And again, in terms of the actual chi-square value, maybe in a future update they'll get this for us, but they'll indicate that chi-square is here, and they make it look like an x squared, but it's supposed to be like a jazzy x. All right, that's a critical value, and the cutoff was 0.05. Oh, I got to change my degrees of freedom, 18. Oops, I hit the back thing there a couple times accidentally. 0.05, but I want it on the right tail. So 0.05, hit OK, and we get that cutoff of 28.869, all right? And so there we have it. And like I said, the previous one, I just kind of glossed over the conditions, which would not have worked out well for me on the AP exam. So let me go back and throw that in there. I'm gonna shrink this down a little bit. There's so many moving parts that it's very easy to lose track of what it is you're trying to do. So in this case, yeah, random sample, we would assume it, 10%. Got to imagine that there's more than 8,300 stolen cars, but maybe not. But I'll assume it anyway. And the expected cell frequency, each one of these values is more than 5, so we're good there. So that's confirmed. And also, just while I'm putting the finishing touches on this, pretty sure I never named this test, right? So just going back here, remember when you're in your inference app, aside from the fact that it says t-test here, which is infuriating to me, when you click on the right one, it'll tell you the title. So always indicate what that title is. They're looking for that kind of stuff to give full credit. All right, so I would chuck that in there. So chi-square, so jazzy x, chi-square test, homogeneity / independence. We're using independence here, so you don't have to write homogeneity if you don't want to. All right, and that would be a two-way chi-square test. There's so many different names for everything that we do that it's very easy to kind of get them confused. But use the numworks to its fullest potential, and I think that'll help you get where you need to go.